Thank you. Well, it's more of a Sarah didn't take her own advice situation. Not good. So past Sarah had already figured it out, but didn't write it down. Yeah. But happy to know that when I made decisions 5 years ago, they were in fact based in theory and not just.
Which actually he spent for some time already at Oak Ridge, then continued as a postdoc at Oak Ridge, and now since research associate. Jordan is enthusiastic microscopist. He'll show plenty of really nice images and spectra, and covers different fields. And I guess won a lot of prizes from especially Microscopy Society of America. Without further interruption, welcome Jordan in this talk on Monochromania.
So, as Matthias said, I'm Jordan Hachtel. I'm from Oak Ridge National Laboratory, and the experiments I'm going to show to you today are all from a technique called monochromated eels. And I want to keep in the focus of your mind that monochromated eels is a technique that had been around for ages, but we've recently had some developments that improved the power of the technique by about an order of magnitude. And it's funny because it wasn't just an improvement of resolution, like new things became possible at this level of energy resolution that were fundamentally not possible to do before. So it's really opened up brand new fields that we could have never even dreamed to look at. And I wanted to go through a couple of them today and show you how new types of science have been enabled by this new technique. So I'm gonna, as an outline of the talk, I'm gonna go over some of the fundamentals of how monochromated eels works and how we do it at Oak Ridge. And then I'm gonna go through 3 different topics. First, I'm gonna look at nanofluidics, which is something Matthias and I have in common. And I wanted to show you our newest results on this, and that's all like really fresh, unpublished stuff that we're very excited about going forward. And then I also wanted to talk about how some of these monochromated eels experiments could be applied to biological materials and how we can look at whole sample biological specimens and get high spatial resolution analysis. And then I'm going to end up about how we can really, really take it up to high spatial resolution and do atomic resolution and atomistic analysis of phonons in ceramics and complex oxides. So starting off with the intro. The technique I do is called scanning transmission electron microscopy, which is different from standard TEM in the fact that we take a converged probe and raster it back and forth across the sample. The idea here is that we're acquiring data from each point individually rather from the sample as a whole, and we're correlating the signal on various spectrometers and detectors with the probe position as opposed to doing any actual imaging. And the type of analysis I like to do with this is electron energy loss spectroscopy. And in this, we take the transmitted beam and we put it through a magnetic prism. What this will do is it'll disperse the electrons by how much energy they had or how much energy they lost going through the sample. This will be projected onto a detector, and individual peaks will correspond to energy excitations in a sample where they gain that energy in the sample by losing electrons or losing energy from the electron beam. And so there's a whole lot of different things you can do with this. And the most conventional one is called core loss eels. And in this, what you primarily use it for is compositional analysis. And the reason is that the core shell electrons in any individual atom have very specific energies away from their valence band. So essentially, you can do something like go to a transistor gate stack, and you can go to 532 electron volts in your eel spectrum. And at 532 electron volts is the oxygen K edge. So when you see this sharp onset of intensity in your eel signal at 532 electrons, that uniformly corresponds to the presence of oxygen in your sample. So then we can go through each individual probe position, measure the intensity of our signal at 532 electron volts, and produce a direct map of the oxygen within the sample. And so this is the conventional way to do eels, and it's really powerful, and there's tons of work that's been done on it. But that's not what we do. Well, it's not all we do at Oak Ridge anymore. And the reason is because all of these high energy or core loss excitations are very high energies. So what the energy resolution of the technique is kind of doesn't matter. So how we define the energy resolution in EELS experiment is very nicely quantified by looking at the zero loss peak. Now this is the elastic scattering peak or the non-interacting peak, and essentially it's in every single EELS spectrum, and it corresponds to all the electrons that did not lose any energy as they went through the sample. So either only scattered elastically or didn't even hit it. So in a perfect microscope, this would be a delta function, exactly at zero, because every single electron will have lost zero energy. But in practice, it's about 300 millielectron volts wide for a cold field emission gun. And this just corresponds to the fact that you cannot actually extract electrons out from an electron gun without creating some spread in those energies. And this 300 millielectron volts is that spread of energies. And so, while if you're comparing 532 electron volts to a spread of 300 millielectron volts, no problem whatsoever. It doesn't even matter. Well, what if I'm interested in something at 100 to 200 millielectron volts? Now this spread is prohibitive. And it's not just that. This tail of the zero loss peak provides a tremendous background where even if you have a signal, there's no chance of you detecting a subtle excitation on top of this massive background from your elastic scattering peak. So this is why we need monochromation. So what we do is we take our 300 millielectron volt zero loss peak, and we basically put it through two EELS spectrometers that have just been stapled back to back. The first EELS spectrometer creates the zero loss peak at the midplane of the monochromator. So it essentially just disperses the beam and creates this zero loss peak in real space. Then we have a physical slit that only selects a narrow band of those electrons, and then we undisperse it and pass it back into the column. And this allows us to go down to around 5 millielectron volts in our instrument. And this is the place where the instrument we use really had an order of magnitude improvement. This type of technique had been used to get around 80 to 100 millielectron volts in the past. And this company, Neon, which makes the instrument that I'll be talking about today, was the first one to get below 10 millielectron volts. And so this was really, really totally game-changing because you could do something like look at, and so a key point is, I got ahead of myself. You can really see the effect of monochromation by looking at the effect of varying the width of this slit. And so even here, while we haven't narrowed the beam too much, you can see we've really dropped the tails. So that's the other key part of this. Is it's not just the improvement in energy resolution, it's the reduction of background in this area. And we have all this control to go down further and further and further and get more and more reduction. Do you have a question?
Yeah, I do have a question. There's no sample in there yet.
There's no sample. This is in vacuum.
This is the beam. So this is before that green cone over there.
Yeah, no, so this is all pre-specimen. So this, it comes straight, like if the instruments are bottom up, so the electron gun lives down here.
Okay.
And so my field emission happens right here, and then that goes directly into the monochromator, and then that will eventually go up into the sample. So we're monochromating before we get to the sample.
Thank you.
And so when we're down here, we've not just improved our energy resolution, and we've also reduced our background significantly. And the effect of this can be really quite dramatic. And I wanted to show you a comparison of two different levels of monochromation, 6 and 12 MeV. And this may not seem like a lot. You can see certainly in terms of the background reduction, it's pretty comparable. But now let's take a look at what the vibrational spectrum of an amino acid, L-alanine, looks like at these two different levels of monochromation. And we see that it's a totally different world. And this is the reason why this getting down to this sort of 5 MeV level was so transformative. Because even at a level of 12 MeV, and where you can detect these vibrational peaks, there's still this wealth of vibrational information that was always in your sample that you just couldn't detect because you were at 12 MeV rather than 6 MeV. And so this is really why these instruments have been a sort of tremendous leap forward. And this is a picture of our instrument. This is the electron gun down at the bottom. It is a monochromated and aberration corrected stem that we call the max stem. Normally I say, normally I say, the max stem.
No, that's better. Okay.
So yeah, as I said, the electron gun's at the bottom, and this is the monochromator module right here where all the magic happens. And immediately afterwards, we put it through an aberration corrector. So this allows us to improve the spatial resolution of the electron beam coming out of the gun. And then our sample is right up here. And then our imaging detectors and our spectrometer is up here. And we can operate at multiple different accelerating voltages. We can get sub-angstrom spatial resolution. We can operate at 30, 60, and 100, and even get atomic resolution at 30 keV, which is important for a lot of two-dimensional materials that can't take a lot of high-energy electrons. We have very specialized detectors for 4D STEM, which is not something I'll talk about today, but is another very powerful ongoing revolution in the field of electron microscopy. And most importantly, we have this monochromator that gets us down to 5 electron volts. And so with that, we are ready to actually start learning something with this technique. And the sample we're going to look at first are these carbon nanotubes filled with water. Now, this is a collaboration through the CENT EFRC. It was brought to us by Arun Majumdar and Shintong Xu from Stanford University. And then I roped my old PhD advisor, Sok Panelides, and his new postdocs in to do some of the theory for us. And I think we've really found some pretty important results on this system. And so basically what we're looking at is carbon nanotubes where we've now filled them with water. And this is a very important topic for nanofluidics because the type of transport you get in here has a lot of applications in biotechnology, desalinization, and it's just a kind of difficult system to study because of the low dimensions involved in it and the low cross sections and widths involved in it. But so STEM actually gives us a real advantage to look at these systems. And I wanted to start by showing you how water looks in the STEM. So the first experiment I'm going to show you is in a traditional liquid cell. This is a silicon chip with silicon nitride windows, and there's just a spacer and allows like sort of hundreds of nanometers of water to be present in the sample. It's kind of difficult to use because the water runs away from the electron beam. So you take one quick image and it looks like this, and your next one looks like that, and so on and so forth, and the water is always running away from you. But eventually you can chase it into a corner, stick your beam on it, and get a sample and get a spectrum. And so what we see here is two peaks. One at 420 electron volts, which is the well-known OH stretching mode of water. The other one is also fairly well known. This is the CH stretch mode. And this is because all samples in the electron microscope are dirty, and especially gigantic samples where you can't bake them and clean them beforehand, which is the case in these silicon nitride grids. We have a lot of hydrocarbon contamination on the surface that accumulates under the beam. So we always see this sort of double peak structure when we do the silicon nitride window experiments. But you can see that the key thing is this OH stretch mode at 420 electron volts. But now we want to look at some CNTs. And so the first sample I'm going to look at, we're going to look at carbon nanotubes, which you can see like tracing through this sample. And it's just on a silicon grid with a bunch of very small holes. We can go into a STEM imaging mode, and you can see it not super easily, but definitely nicely enough to make sure you know what you're looking at. And we can see the peak extending through this area right here. So we can put our beam in this hole right here, and we can see a spectrum. Here we're going to be dominated by the vibrational spectrum of silicon because we really strongly interact with the surrounding silicon. That's why you start off grabbing a reference spectrum away from your sample so you know what the background signal you should be looking at everywhere looks like. Then we put it next to the sample, and we see a pretty significant change right here in that 400 to 450 MeV region. But the interesting thing about it is that if you look at 420 electron volts, which is the well-known frequency of the OH stretching mode, that's not where we're seeing anything. And we're specifically seeing nothing here. And you have to go up to 460 electron volts to see this peak. But this is also a well-known value of the water vibrational spectrum. And this is the free OH stretch mode, which is traditionally only seen in water vapor. And this corresponds to, instead of having two oxygen-hydrogen modes, vibrational modes going like this, it's just one going like that without knowing what the other's doing. And that's traditionally only seen in water vapor. So we're seeing a spectrum in the water-filled carbon nanotubes that is more akin to water vapor than it is to actual water. So this is surprising in and of itself. But now we can use our combination of spatial and spectral resolution that we have in the electron microscope to help understand why we're seeing this. And so one of the things we had to do was we had to go away from this type of sample. And the reason is I can look at one of these tubes in one of these holes and I can see my nice 450 MeV or 460 MeV peak. But then if I go to a more TEM-like mode where I'm more sensitive to the phase contrast, I can see something unfortunate. I don't just have one nanotube here. I have some bundle of TEMs, or some bundle of carbon nanotubes here. So I don't really know where I think this signal is coming from because it's a little bit delocalized. We know we're seeing something from this bundle, but what we're actually looking at within this bundle is not particularly clear.
What's the radius of these nanotubes?
So the radius of the nanotubes can be anywhere from 1 to 5 nanometers, and we can have varying numbers of walls as well. And this is one of the reasons we also don't like studying it like this, because when you have this bundle, you can't go through and measure the inner diameters, the outer diameters, the number of walls, because there's too many things overlapped on top of each other, so you can't actually see what's happening in this sample. So Matthias here specifically developed this new protocol about how we could create these nanotubes in a sparse matrix so that we had a much higher probability of being able to find individual nanotubes, and we could isolate them much more effectively, both for Raman and for electron microscopy. So essentially what he does is he grows them from these catalysts, and they're millimeters long. They extend across the silicon nitride window. We do a fib cut through there to open up the side of the nanotube, put it in a humidifier, which allows water to infiltrate the nanotubes. Then we reseal it with Torseal, and now we should have a completely sealed water and nanotube system where we have nice isolated carbon nanotubes. And so this is what it looked like before on the small hole silicon grid, and this is what it looks like on this larger, more structured silicon nitride grid. And we can still go in and find these individual spots. And so what you can see is it's now pretty straightforward to find these CNTs. I feel pretty confident from these STEM images that you're looking at just a single tube at a time. And I want to show you 3 spectra from 3 different tubes. The first one looks like this. And this is what the majority of the tubes look like. You see a totally flat background. It's slanted because this is the tail of the zero loss peak, even here, extending out into the higher energies, but no discernible signal anywhere in the water vibrational regime. Then I can put it on a different tube, and I can see a spectrum that looks like this. And we once again see the same thing we saw in the other sample, which is this 460 MeV peak emerging. Then we can put it on yet another sample, and shockingly, now we're suddenly seeing this 420 millielectron volt peak. And just comparing to the bulk water measurement, it sure looks a lot like pure bulk water in terms of both the frequency and the line width of the vibrational excitation. So what's going on? Why do we have these disparate responses, especially between these two? This one just looks like it's empty, so we don't need to think too much more about that. But why do we have such a different response between these two? Well, one of the key things that people understand about these water and CNT systems is that there's a strong diameter dependence on the structure of the water inside the tube. If you have a reasonably large inner diameter, the water in the tube should behave very much like bulk water. But when you go down to narrower and narrower diameters, the confinement or the steric effect that the water has, or the tube has on the water inside, forces the water into these ordered structures or these weird orientations where it can't actually live in the bulk water form. And if you can press down even further, you can get it down to like a 1D chain of molecules too. So the diameter dependence is well known to be extremely important here. So let's go back to these two tubes that had such a different response. Just to remind you that these are the two tubes. And then let's go into a bright field TEM mode where we're really sensitive to the inner diameter of that tube. And now that they're nice and sparse, we should be able to measure that. Here are the TEM images from these two tubes. And what you can't maybe see immediately is that the inner diameter of the one with the 460 MeV peak is around 1.4 nanometers. And the inner diameter of the one with the 420 MeV peak is about 2.3 nanometers. And this actually really, really nicely corresponds to the theoretical predictions of where you should transition from these ordered structures of water to more bulk-like water. So we really think this is a strong indication that we can use the vibrational response detected in eels to understand the structure of the water inside the tube. But we can even go one step further. Let's just do a little bit of background subtraction to make this look a little nicer. But we can also use the vibrational fine structure that's given to us by having this ultra high level of energy resolution. So we don't even need, it's not just the peak position, it's the peak shape we're interested in. And let's start looking at some DFT simulations of what water would look like in different circumstances. So this is the work done by Shin, DeLeong, and Sock at Vanderbilt. So first you simulate bulk water, where it's just a unit cell of water molecules that looks like this, and you can extract the vibrational spectrum. Sort of looks exactly like what you'd expect, peaked at 420 milli-electron volts. Actually a very nice match in the line width between these two peaks, which I was pretty pleased with. And you can really understand it a little better by thinking about the relative orientations of the molecules with respect to one another. So essentially, let's think about two neighboring water molecules inside the CMT. There's going to be an oxygen-oxygen distance between each molecule and its nearest neighbor. There's also going to be an orientation with respect to the oxygen-hydrogen bond nearest that, or by that nearest neighbor. And if you look at what this orientation dependence is for bulk water, they're all very nicely localized right here in this bottom left corner. So it's effectively zero angle, so essentially the hydrogen bond is pointing directly at the next oxygen atom, and the spacing is about 2.7 angstroms. Now let's do a simulation of water inside a carbon nanotube. And so here, to make the simulation a little easier, we've frozen all of the atoms around the side of the tube. And we've only allowed the water molecules inside to relax. And what you see is a split of this bulk water-like response into this bimodal distribution, where a lot of the water molecules have remained in this bulk-like state, but many of them have gone to this new preferred orientation, where they're now sort of pushed off into an unfavorable orientation. And this is what's generating this free OH stretch mode, because they're now bouncing off towards the carbon nanotube wall and not towards the other waters. So they're behaving very much like water in an interface rather than water in water. However, this isn't what we see in experiment. In our vibrational spectrum here, we very clearly see a large, broad peak at 420 milli-electron volts and an extremely sharp, narrow peak at slightly above 460 milli-electron volts. And in our eels, we very clearly see one single peak distribution in the vibrational response. So what happens if we let these atoms in the nanotube vibrate? Well, a lot of weird things happen. Essentially what happens, and I have a video that should play, is in the rigid nanotube case, the water molecules can bounce into an ordered structure where they can all find a preferred orientation with respect to one another. So they can basically find a way to sit and still be like bulk water, even in a very confined space. But this requires a rigid boundary condition so that the water molecules can order properly. Once we remove this rigid boundary condition and allow the walls to be vibrating in pace with the water inside the tube, the water's molecules cannot find a preferred orientation because the preferred orientation is changing as a function of the vibrations in the tube. And the effect is that there is now no singular distribution, much less a bimodal distribution, of any of the water in the tube. And now all the water molecules just take on this totally disordered state because it cannot find any preferred orientation inside the tube. And this results in a single peak that is peaked just under 460 milli-electron volts, which matches extremely well with the vibrational spectrum we detect in eels. And the most important thing is the instrumental broadening is much, much lower. Our energy resolution is much lower than the actual line width of these peaks. This is the zero loss peak that we can use to quantify our energy resolution. And so you can see we have instrumental broadening right here. For these spectra, it's on the order of like 8 or 9 millielectron volts. But even still, the width of this peak is 40 or 50 millielectron volts. So we know this is the real line width of the vibrational modes inside the water. And we know that we're not looking at this. We're looking at something like this. So this is a way we can use EELS to really learn about the structure of the water inside the tubes.
How big is the spot? I mean, how many molecules are?
So it's funny you should ask that. The density
People say
is one of the things we spend a lot of time thinking about. And because this is actually one of the things in the nanofluidics community that it's actually very hard to determine is how many water molecules per unit length of this nanotube should there actually be. And so we spent a lot of time thinking about that. And the first thing we did was we compared this rigid tube versus vibrating tube analysis for 3 different densities. This is 0.6 grams per centimeter squared, 0.4 grams per centimeter squared, and 0.2 grams per centimeter squared, where bulk water would be 1 gram per centimeter squared. And so you can see in all 3, it takes on this bimodal distribution. And the only thing you vary by changing the density of the water is the number of molecules in this weird off normal orientation with respect to the water versus the ones that are in a bulk water-like orientation. However, the effect of allowing the water molecules to vibrate is also uniform between these densities. Once again, I can change the ratio of more bulk-like to more non-bulk-like ones, but the effect of allowing vibrations is to always break this bimodal structure and allow a continuous variation of the water molecules' orientations with respect to each other, and the removal of 2 peaks to 1 peak centered closer to 460 millielectron volts. So while we can't tell directly from this, we show that this effect is independent of density. So regardless of what density we are actually witnessing in the microscope, we know that this is a mechanism that's driving the water's structure inside the tube. And so the way we can take another step forward is by going down to cryogenic temperatures. And so we have a side entry Gatan ELSA holder. This is a very powerful holder in the sense that it has a huge dewar. So we can do 8 hours. We have 8-hour hold times at liquid nitrogen temperatures. A lot of the first generation of cryo holders only had 2 to 3 hour hold times. So they were very difficult to use, but these new Gatan ELSA holders are very, very stable for very long periods of time. And we can now put these samples into the ELSA and actually do the cryo experiments. Right. For some reason, the animations on this one are loading a bit slow, so I'll probably be a bit off in my timing. All right, so here's our first cryogenic experiment. This is on the 460 millielectron volt tube. The yellow spectrum is the room temperature spectrum. And this green one down here is the cryo spectrum. And so maybe you can see some changes in the line shape, like my eye can track maybe a positive second derivative there, and like maybe a more linear shape to the tail there. But that's actually quite difficult to tell at this level of signal to noise. So we don't really think too much about that. And we can do the vibrational calculations at 300K and 100K for the 0.2 grams per centimeter case. And we actually see something that looks pretty similar, where we see a strong positive second derivative here in the line shape and the room temperature, and then something maybe a little more linear on the cryo experiment. But then when we go to the higher densities, something interesting happens. And essentially what we see is that as we go down to cryo temperatures, we should be suppressing the vibrations in the tube. So we should be returning our vibrating tubes into something that looks a lot more like the rigid tube case as we go down to lower and lower temperatures. However, this function, or the number of water molecules in the tube, strongly influences how this will affect the net vibrational spectrum. And you can see for the higher densities, like 0.4 and 0.6, we do break into this bimodal peak structure, indicating that now the water is finding ordered states. It is going into these periodic sort of like polygonal orientations where most things are operating like bulk water and only a few molecules are operating as vapor water. But that isn't what we see in the experiment. So now, granted, my collaborator would want me to be very insistent that this needs validation, right? We have no direct way to measure the density of the water inside the tubes beyond this. So how accurate this comparison is for determining the density of water is yet to be seen, because a number of factors could affect the vibrational fine structure. So maybe it's not as simple as the case we're painting here. But we can really see by this comparison that our data is consistent with these very low densities of water inside the nanotubes, and it is not consistent with the higher densities. So for us, we really feel this really is an indication that we can use vibrational spectroscopy to look at the density inside carbon nanotubes. And there's other interesting things that happen. We could perform the same experiment on the 420 MeV tubes. And what you can see is that ice has its own unique effect on the OH vibrational mode, and especially bulk LH ice has a peak, a well-known peak at 400 millielectron volts. And when we took the peak that was vibrating 420 millielectron volts to cryogenic temperatures, we saw the emergence of this secondary peak at 420. And the nice thing is when we went back to room temperature, we saw that peak go back to normal. So this looked very much like we had a strong indication of a reversible phase transition. Now, I was a little hesitant to talk about strong statements on the other two because we did this experiment a few more times and we did not see the same exact thing every single time. And so I shouldn't have done it in this order. All right, I'm just going to show this one next and we'll get to what's happening over here later. So when we did another tube, we saw another nice peak at 420 millielectron volts. We do the cryo experiment. We do not really see the emergence of a secondary peak at 400 millielectron volts. Now, if you squint your eyes real hard, it does kind of look like there's maybe some shoulder there that's not present there, but that's not really what I would call a 5 sigma discovery. But the point is that there's a number of different factors. This tube has a larger diameter than the other one. This was 2.3. This was around 3.5 nanometers. So the fact that the diameter is different could have a very different effect. There's also different phases of ice. You can have amorphous ice. You can have other crystalline forms of ice. So we don't know that this isn't an indication of a reversible phase transition. It's just an indication that something crazy might be happening. When we went to this other third sample we looked at, it definitely indicated that something other crazy might be happening. When we looked at this one, we saw the peak at 420, and it had this secondary peak at 380. And when we went out to cryo, that peak red shifted and that peak blue shifted. And I have no real good explanation for that. But what I will say is the only way we were able to do these calculations for the larger tubes that behave bulk water-like, it's really computationally expensive to do the calculations. We can only really do nice, expensive calculations in the low density case for really low diameters of the tube. We can't, it's just computationally insane to try and go up to 2.5 nanometer inner diameter and then do rigorous molecular dynamic calculations. So all our theory team could really manage was doing this mixed model of water and ice. And what they saw is that if you calculate the vibrational structure of a mixture of ice and water, you do see peaks at 400 and 420 at the same time. But you also see a bunch of other peaks down here in this 360 to 390 MeV range. And that's right where we saw these peaks as well. So this is an indication that there could be many different types of ice present in the sample that behave in many different strange ways. And really, to me, it's an indication that there's a lot of more work to be done here to fully understand the different temperature dynamics at play. And just to finish up, there's other crazy things that happen too. And I'm sharing them to be totally academically honest. Wouldn't want to hide any of the weird parts of my data that I don't quite understand. Starting over here. We've looked at a lot of tubes now, probably like 70 or 80 tubes. 90% of them are just empty. They just show no signal whatsoever anywhere in the vibrational response regime. You have the peak at 130 for the silicon nitride, and that's it. On the ones on the silicon, the small hole silicon grid, they were all uniformly at 460 milli-electron volts. We found none that showed the 420 milli-electron volts one. On the silicon nitride one, we found 3 or 4 tubes that had this 420 milli-electron volt peak. But I also found 2 tubes that didn't have a peak at 420 or 460, but did have a peak at 490 milli-electron volts. And no one anywhere on our team has even the slightest clue what could be happening here. There's no theoretical predicted ways that your OH stretch can somehow make it to 490 MeV. This is just not something that has come up in literature. So we really don't know what's happening in these samples. There's something very, very strange happening that's not happening in every single tube, but 490 was repeatable. And so that's weighed on my mind heavily. And especially given the secondary part. This tube, pay no attention to this. This is swapped around. So this is the spectrum from the small silicon, whole silicon grid one, the first one we looked at. And you can see we really have no peaks other than this very strong peak at 460 milli-electron volts. But when we look at the ones on the silicon nitride grid, we see all of these additional peaks. And the crazy thing about it is these peaks, other than this one, will vary by position on the tube. Like we can go to a different part of the tube and those peaks will have different intensities and different frequencies. And the 460 will stay the same, but those other peaks will vary quite significantly. And what's more alarming is this is the cryo measurement on the 420 MeV tube at room temperature and cryo, and you can see, in addition to this phase transition of the emergence of the 400 MeV peak, all of these other peaks just shifted in frequency as well. And so we also have, go ahead.
Is the relative intensity of the peaks meaningful?
I would say so. So there'll be some bias towards lower energy, like you have a energy of the excitation versus primary energy of the electron beam dependent. So lower energy things are more easily excited than higher energy things, but that should be a continuous function. So when you see something like this being weak and that being strong, that is a meaningful intensity difference. And we see strong variations in those relative intensity changes. So this is also something we don't, like it doesn't come out of the theory at all. Like the DFT calculations show no peaks at these values, but there is some IR absorption literature that shows that water has weird absorption bands up at these frequencies. So the key message, water's crazy and it does crazy things. And I think one of my favorite things about this system is how crazy it is and how much we have to learn about it. So that took...
Can I ask one more water question?
Yeah, fire away.
What pressures are inside of the nanotubes? Like where in the phase diagram are we? Do we know?
Well, my assumption was we'd be somewhere in the liquid water phase, but I have no idea. Okay. And that's the other question about the vapor versus liquid water, right? Like maybe that's a pressure phenomenon rather than a density phenomenon. How would you really distinguish between these things when you don't have a direct measurement other than this comparison to theory? But the density or the pressure inside the microscope itself is 10 to the minus 9 torr. So we're at extremely ultra high vacuums. So I sort of imagine the pressure can't be that high inside the tube, right? Like,
Yeah, I mean, there's a set of literature of like these encapsulated, like high pressure, like bubbles, right? So I don't know.
Yeah,
I guess it's anybody's guess.
yes, exactly. And so how you'd measure it and how you'd validate those measurements is something I'm very interested in, but I don't have a great answer for right away. So that module took quite a bit longer than I had initially intended. I had intended this whole talk to be 45 minutes, and we're at 39 minutes right now. So what do we like between biological materials or atomic resolution vibrational spectroscopy?
Atomic resolution.
All right, first answer gets it. So we're going to just skip through this. I will give you a quick summary of our results, which will be nice and easy to summarize here. In biological systems, the big question is whether or not we can get enough information per dose in biological specimens to learn anything meaningful. Because while the electron beam has all this nice spatial resolution, biological materials don't like being irradiated with 60,000 volt electrons. So they die pretty quickly. But if you do very, very fast imaging, and what we've done here is we've taken sequential spectrum imaging over a large area with 100 microsecond dwell times per pixel to really minimize the dose. If you go really, really fast, you can actually get enough information over a large area to meaningfully sum your signal across a high spatial resolution feature. So essentially, each color here is a mask that then corresponds to a distance from the interface in this graph. And, well, I could grab any one of these pixels and it would be completely meaningless noise. You integrate all of them and you actually get a definitive signal. And so we can then use this to do a sort of spatially delocalized interface line profile. And we can see that we can detect localized changes with a spatial resolution of around 15 nanometers. So this preserves the vibrational information of the biological specimen. So to me, the main message of this result was, can we go fast enough with good enough signal to meaningfully probe beam-sensitive biological specimens with nanospace resolution? The answer is yes. Now, on to atomic resolution vibrational spectroscopy. So I talked briefly about how these, there's a little bit of delocalization in these modes. And that's because the electron beam interacts with the sample through a Coulomb effect, right? So the electric field of the electron beam sees the sample and you interact with it. And this forms a delocalized interaction that you can use to probe vibrational modes. But sometimes you don't want delocalized information. Sometimes you want localized information. And we can actually get this by controlling the experimental geometry of the collection. So essentially, normally you collect this is what's called a convergent electron beam diffraction pattern. And so essentially it's the angular space distribution of your diffracted electron beam, your diffracted electrons. So the width of this is the convergence of your beam. So more converged beam is more angles. And normally we live right here in the central bright field disk that corresponds to the optic axis of the diffraction. And so you just do that because that's where all the electrons are. So your signal to noise is best here. But that's also where all the delocalized information is. And so what you can do is you can go out to these higher angle informations. And in order to get out here, there has to be quite a lot of momentum transfer into the electron to get it out past the optic axis. And this requires a more Rutherford-like scattering event. And this is what we call impact scattering. And this is localized to the individual nucleus that generates the scattering. So it's a totally atomically localized phenomenon. So we can, instead of collecting our zero loss peak or EELS on axis, we can collect it off axis and preferentially bias our collection towards these high angle impact scattering events and get highly localized vibrational information. And so this is also with my postdoc Eric Hoagland and once again Sok and DeLeong and my postdoc's former PhD advisor Patrick Hopkins. We looked at two different systems: superlattices of STO and CTO, which is an interesting system because of the octahedral tilts that are different between the two systems, and of STO grain boundaries. And grain boundaries and the dislocations therein are one of the canonical defects that affect the vast majority of materials and are hence the most important to understand at new levels. So starting off with the STO-CTO, what we were really interested in was the effect of the periodicity in this superlattice. So you can compare a 27 by 27 unit cell superlattice to a 2 by 2 unit cell superlattice. And what Eric found by doing selected area electron diffraction was you can see diffraction peaks that are present in the high period superlattice, the SL27, that are not present in the short period superlattice. So what we know is there's symmetries in the crystal that are present when a large period is in the superlattice that are gone when it's in a short period superlattice. And so he did these DPC measurements, which allows us to measure the octahedral tilts. You can see in STO, we see no octahedral tilts, but then in the CTO, we can actually see these oxygen atoms split. And that's because the titanium octahedra rotate, and then in projection, you have a splitting between the two oxygen atoms. And so we can just straight up measure this angle by measuring the distance between the two oxygen atoms in the DPC image. And he found the following for the different superlattices. When you have a very large period unit cell, it goes from basically 0 octahedral tilt in the STO to around 10 degrees octahedral tilt in the CTO. Bulk value of CTO, bulk value of STO. Well, we have about a 4 angstrom interface layer where it is neither at the bulk value of STO or the bulk value of CTO. And when you go down to 4 unit cells, now each period is about the width of this interface. So you see, instead of it going from one to the other, it's now just sinusoidally oscillating between the two bulk values. And when you go to 2 unit cell superlattices, now the interface width is larger than the period of the superlattice. So you never go back to bulk values. And in fact, you're pinned specifically at about 6 degrees of octahedral tilt, which is right at about the interface value of the superlattice. So basically, you've created 3 different scenarios: a crystal with interfaces, a crystal dominated by interfaces, and a crystal of interfaces, where now it's an entirely single material that is just made of the interface. And this comes through in the vibrational spectroscopy as well. We do these off-axis line profiles, and there's a couple of things you can see from these. One, we have variations in the EELS signal that are consistent with the variation in the dark field signal. So we've really removed the delocalization of these effects, and now we're really seeing the localized vibrational response. But if you look really closely, you'll see there's fundamental differences between the STO and CTO layers in the 27 and the 4 unit cell superlattices. But really, we just see some slight intensity variations in the 2 unit cell superlattice. And you can really see this by going through and binning all of the different pixels by their position with respect to the CTO, the STO, or the interface. What you can see is we see quite significant variations, especially here and here on the large period unit cell superlattices, that have really come together and are totally uniform in the short period superlattices. So we can really see crystal with interfaces, crystal dominated by interfaces, and crystal of interfaces is represented in the vibrational spectrum as well. And then lastly, you can look at the macroscopic properties and the phonon scattering, and they also show the exact same effects. As you go from large period to short period superlattices, you're increasing the number of interfaces. So you're essentially creating more phonon scatterers, so you should decrease your thermal conductivity and decrease your phonon lifetimes. But then once you hit this interface width on the periodicity, essentially you create a single consistent material that's now a new material made up of the interface, and the thermal conductivity actually goes up at these low superlattice periods. So we can see that in terms of the chemistry, the vibrations, and the macroscopic properties, we get all 3 of these regimes. I'm going to quickly just go through the grain boundary results because I think these are really nice. You can do compositional EELS the same way we talked about at the start of this talk, and you can map the oxygen, you can map the strontium, and you can map the titanium. So you can understand the chemistry present in these materials. see that we're pretty much consistent in terms of our oxygen content, but we're strontium poor at the grain boundary dislocations and titanium rich. So we know at these dislocation cores, we fundamentally change the chemistry of the material. So now when we go through and we do the off-axis experiments, we can see these individual dislocation cores light up, and then we can do sort of maps about like how far away from the center of the dislocation core. So we can look at representative spectra from the very center and then radially outward masks from each dislocation. And we can see very significant variations in the vibrational spectrum. And so basically what you see is you have two dominant peaks at around 60 and 90, and then they come in together inside those dislocation cores. And you can really map this effect out nicely and see that we're getting red shifts of the E2 peak and blue shifts of the E1 peak as a function of the individual dislocation cores. And if you really squint your eyes, you can also see that you also have variations between the individual dislocation cores that are much less subtle, or much more subtle than the ones in the dislocation cores themselves. But the real nice thing is that we can compare this to DFT, and we can do theory modeling of the dislocation cores themselves. And we can, this had so many atoms in it, we really had to use the EELS composition and atomic resolution imaging to form a model that would actually relax with this complex dislocation core geometry. But we were able to get it done, and then this allowed us to do a direct comparison of the experiment and the theory for the vibrations of dislocation cores. So here I just do a quick principal component like decomposition to show the base structure of the vibrational spectrum of the bulk STL and of the dislocation cores. And it can really be understood by looking at the black and the red curve here. The black curve, and look at the solid lines, not the dashed lines right now, really shows this two-peak distribution that we were able to see very nicely in the previous ones with the E1 and the E2 peak. But when you do this PCA-like analysis, you see that you don't actually have red shifts or blue shifts of the peak. What we see is there's a new band of vibrational modes that appears in the gap between these two peaks. And you see that it's really just the emergence of additional vibrations between 60 and 90 MeV, not shifts of the 60 and 90 MeV. That's happening at this dislocation cores. And when you do the theory, that's exactly what those dashed lines are. It agrees really nicely. And then also because we have the theory, we can actually go to each eigenmode inside this vibrational band and map it out. So we can now look at individual vibrational modes inside dislocation cores and grain boundaries and really understand it and compare it to theory. So with that, I still have some time for questions, so I'll wrap up very quickly. Monochromated EELS is a really powerful technique that has a lot of really exciting new applications that were simply not possible 5 to 10 years ago. And one of the ones we've really been excited about is the application to nanofluidics. And we think we can use, especially in combination with theory, this vibrational EELS as a way to get at the structure of water and other fluids inside confined spaces. We also have really, or I personally really believe that biology could be one of the places where this has a strong impact, because I think the EELS approach is extremely complementary to the other techniques that are already being employed in bio, and that we can definitely do things to leverage the high spatial and spectral resolution while optimizing the beam damage to information ratio to do some very important work in the biological sciences. And then lastly, the key to all of this is we really do get atomic resolution information out of this. So we can go down to whatever size nanostructure you want. And with a little bit of work, we can get those vibrational modes out of there. So with that, I'll thank you for your attention and let me know if you have any questions.
Okay, are there any questions? Yes.
That was a very nice talk. Amazing technique. In the biological sample, are those cells sealed?
Yeah, so right now we've looked at mostly fixed samples that were fixed in resin, but we've also been pushing towards cryotransfer, and we have cryotransfer set up in our instrument right now. So one of the things we're really excited about moving forward is doing frozen, like vitrified samples in their native form with no resin infiltration and looking at the vibrational spectra there. And one of the really cool things about the way we do this is that because it's all done at ultra-high vacuum, 10 to the minus 9, you don't actually get the same ice buildup on your samples that you do in lower vacuum microscopes. On sort of traditional TEMs, if you do cryo experiments, a small layer of ice builds up as a function of time that really starts to hurt your results. But we don't get that. We can do really long acquisitions with no ice buildup. And we can directly measure that we don't get any ice buildup because we can access the ice vibrational modes.
Can I just about you said these long acquisition times that you talked about your cryocooler or your cryogenics. So how long does each one of those spectra take to acquire?
So the spectra I showed for the carbon nanotubes will be about 1.5 minutes per spectrum. We like to do a huge number of very short dwell times because when you're at super high energy resolution, you're really sensitive to stray fields in the microscope room. So your zero loss peak will actually bounce around very quickly. So what you don't want to do is do one really long dwell time measurement because then all that bouncing around will just be integrated into your signal. But if you do a bunch of really fast measurements, you can then correct each one individually after the fact and get the native resolution of the instrument. And it's all 60 hertz noise that's really killing us. So we can actually go faster than the 60 hertz noise by doing sub-millisecond acquisitions.
Yes.
What determines the variation of the water density in different nanotubes? Is it homogeneous in one tube?
So what I have seen is when we see the vibrational spectrum at 460 or 420 in one spot on the tube, we see that same peak everywhere on the entire tube, like for the whole millimeters long variation of the tube. Those higher energy peaks that I showed at the end that we don't really understand what those are, those will vary quite significantly from spot to spot, but the OH stretch mode itself seems to be very consistent even across the entire tube. And we also know from TEM that there's tons of like small variations in terms of the inner diameter. So I'm willing to bet that like if you got lucky, you could find a place where it went from a small inner diameter to a bigger inner diameter and could potentially see some change in that 460 to 420. Or maybe, who knows, maybe the entire tube would display a different behavior in that circumstance. But
can you in situ tune it, like how you chase the water to one corner? Can
So,
you chase another one?
That's the other thing that I really think is an interesting effect. So we see water in very, very few of the tubes. But it doesn't quite make sense to me that we should see water in like 10% of the tubes. My brain tells me that if it can get into 10%, it should get into most of them, and there should be broken tubes that it doesn't get into or gets out of, or it shouldn't get into any tubes under any circumstances. So one of the ideas I've been kicking around in my head is maybe we only see this peak when it's a completely filled tube. And when it's a partially filled tube, we're actually chasing the water back and forth across the tube. And by the time I get a vibrational measurement, all the water's gone, so it looks empty. But then in a full tube where there's nowhere for the water to go, we're able to measure it consistently everywhere as we go across the sample. But I have no way to prove that that's the case. That's just an idea I've been kicking around in my head.
Thank you.
Maybe this is a silly question, but I think you said you couldn't measure the density like inside the nanotubes directly. Like, why is that? Is that just because it's like within the apparatus of the eels at that point? Or?
Well, so the experimental setup to measure the density of the tube, what would this look like? I would consider maybe we could do like mass spec or something like that and measure the number of water molecules, but how could you do mass spec from this area and really consistently, like really deliberately isolate what signal in your mass spec came from the tube? The problem is that it's just so small, you can't apply a standard density measurement technique. Like you just don't have access with anything other than extremely high spatial resolution techniques to the individual tube. So I don't think there's any reason why it's not like you can't measure the density in the tube. I certainly believe it is physically possible to measure the density of the tubes. It's just coming up with the experiment that would measure the density in the tubes is something I can't think of.
Any other question? Yeah.
Sorry, is there? Can you get other things in there besides water?
I believe so. I think there's no reason why that wouldn't be the case. We haven't done that yet. These are still reasonably fresh, but it's something I think this is probably one of the most promising applications of vibrational eels I've seen. A lot of our initial work was all proof of principle experiments that said, hey, eventually we're going to learn something very interesting from this technique. This has been one of the first ones I've worked on where I feel like we are learning something very interesting from this technique. So I think it's very promising, and there's a lot of different things you could do it. Essentially, the cross-section and measurability of the vibrational modes works out very nicely. So I think you could do systematic studies. You could do parameter sweeps. You could do all of these things to be careful and deliver foundational scientific studies to this system and really learn a lot. We've done the initial measurements, and I presented to you most of what we've figured out from the experiments we've done, but I think more measurements would be tremendous. And definitely, I think new fluids would be a great thing to look at. And also different types of encapsulation, right? Like intercalated materials, buckyballs, zero-dimensional encapsulation. Why not?
Okay, I guess it's time to wrap up. Thank you so much.
I know, try this out.
Do you put your the carbon nanotubes that are made?
I don't know.
Yeah, but is it full? Okay, so there's no chance that there would be any defects or anything like that.
Oh, there could be some.
Yeah.
Because looking at the way some of those peaks were showing up, it just reminded me of some of the stuff that I had done in SunLab with like reduced graphene oxide and stuff like that, and looking at like the nitrogen defects or the oxygen defects. So I was just curious if that would possibly be some of those peaks, or it's just defects in structure that were showing up with a different mode.
So I don't think that's the case, and the reason I don't think is the same reason I've been able to convince myself that it's actually water inside the tube, and it's because we don't see it on everything, right?
Yeah.
Like we only see it on, like when we see the water peak, we see these other peaks, and when we don't see the water peak, we see none of the other peaks. So for me, this can't be defects in the nanotube, because that would be something that but I guess your point is like, could defects in the nanotube be affecting these peaks? So we only
Acceptance of whether or not they're taking on water.
So that's actually an excellent point. Let me show you something real quick.
And could you take a moment to use one by?
Yeah.
So we can do this spectrum imaging on the tubes, right? And so this is the empty tube, and this is the filled tube. But we see quite uniform intensity, and we can see that on the other ones as well, right? Like, so you'll have spatial variation of maybe like 20 to 30 nanometers, but it'll just be one peak slowly going down and the other peak slowly going up.
Yeah.
So what I've been telling myself is that I really think this is a strain effect, or something like done by the tube conforming to the complex topography of these silicon nitride grids. I would think if it was a tube, you would see very localized, or if it was a defect, you'd see something very localized, where you'd see one spot where you saw this peak light up like a Christmas tree, and then it would vanish. And that's not really what we see. We see the peaks everywhere, and we see them gradually changing from one area to the next. So to me, that's not consistent with defects. That's consistent with some strain or geometric effect, because that's the sort of scale by which we.
Do they show up fairly regularly then? Because then it would
Every
show up as part of.
We never see on this sample. We never see the water peak without seeing the other peaks.
Okay.
We always see all of them, and they're never the same. Only these peaks stay the same. None of the other peaks ever appear at the same frequency.
Just curious.
really cool.
That's, yeah, it was really neat. I took a bunch of notes for me.
Yeah.
Stuff later.
I'm glad you liked it, man.
Oh, and the other random question with the wells that you were showing from the two overlaying things with the it's been a long day. I'm sorry. The wells with the octagonal shifts and changing. If you were to pattern that out for something, you could create an entirely different chemical environment in those to do particular like chemical reactions, like CO2 reduction, something like that, with some regularity, I would think, because you'd be able to control how they disjoint essentially.
So maybe, but I think for things like CO2 reduction, you're more concerned with your surface area rather than your like actual vibrational response, right?
It depends on where you're doing the either the reduction or.
That's hard for me to think about. I don't really have a strong sense about whether that would work. Definitely the philosophy behind these superlattice materials is tailored thermal materials. So they're thinking more for vertical devices, right? Like instead of having a gallium nitride layer, maybe you have two unit cell superlattice, STO, CTO, and then you can tune the thermal properties in a vertical device. But the sort of idea is that this is millimeters, if not inches, this direction, and nanoscale this direction. So that's where the system is designed for. How it would work in sort of lateral nanostructures, I haven't really thought too much about.
Yeah, because it just put me in mind, especially once you showed like the line of them. Like if you laid it down and put a flow rate over it, you'd have a bunch of unique little reactors where things could happen.
But also, these are all grown by PLD. PLD is good for growing up, not out, right? Like, so how to design such an infrastructure where you have, that's an interesting thought. Maybe you could pattern something.
Yeah. Just that's where my mind went. So I figured you saw, right?
Yeah, if you took him to use some by, and then like you can talk to them afterwards if you can come back home. We can meet in my office and then pretty very excited. How are you?
Yeah, great.
Yeah, no worries.
or like the lobby.